Hello. So today we're gonna start with a new chapter. Okay. So far we have been dealing with the crystals that are at temperature which is absolute zero. At absolute zero, the crystal is considered of a lattice plus a fixed basis. That is, all the atoms in the basis are fixed. They don't move with time. Okay. However, this is really not so much happening in real life. In real life, there is some change in temperature. Okay, and this change in temperature will cause the atoms to vibrate. Okay, in this chapter, we are going to consider these vibrations. We are going to introduce the quantum unit of crystal vibrations, which is called the phonon. Okay, so we will no more talk about a crystal which is just crystallized, it doesn't move, everything is stuck in space. No, we are gonna introduce temperature, and with the introduction of temperature, the lattice points will be moving slightly, okay, and they will introduce what is called a phonon. Okay, we will start by taking vibrations of a crystal with monatomic basis. That is something like just a sodium crystal or silver crystal. Okay, so it is made of monatomic basis, only one atom in the basis, and we will consider only a chain of identical atoms, each of mass m, where the equilibrium spacing between them is A. So the equilibrium spacing between them, that is, if the crystal is at rest, the space between two lattice points is A. However, here, this is not always the case. There will be propagation from A, sometimes less than A, sometimes more than A, okay? Because here we will consider that they are connected like springs, and there will be slight oscillation of each mass. So in our simple model, we are allowing motion of the masses only in one dimension. We will not assume that there is also motion upward and downwards. We will only talk about the longitudinal motion of the chain. We are not going to consider the transverse motion, which is perpendicular to the propagation of the atoms. If the system is at low enough temperature, we can consider the potential holding the atoms together to be quadratic. Here, I just want you to remember Hooke's law. This is very, very simplified form. Hooke's law, if you remember it, we had that the force is equal to minus K delta X. Okay, that is if I have a spring and I compress it slightly or elongate it slightly, I can get the force F by the formula minus K delta X, and we could calculate the energy to be half K delta X squared. Okay, so here is what we mean here by saying that the potential holding the atoms together will be quadratic. Okay, so the energy will be quadratic. Here we will not call K the spring constant, we will call it C. Okay, so the force that makes this atom moves to this side or bring it back this side is C times delta X. This we will not call it delta X, we will call it delta some other thing. Okay, so just for your information. So let's erase this. So because of the quadratic potential and thus the relation to simple harmonic motion. So if you remember that this will be like simple harmonic motion. Now consider an atom of mass m with a deviation us. So this x, instead of x, we said minus K delta X or half K delta X squared. Instead of X, we will say US. Okay, so delta X will be US plus 1 minus US. Okay, or US minus 1. We limit the interaction to the nearest neighbors. We will not say that this mass over here will interact with this mass over here. Okay, so we will take this unit atom S, and we will say that it will interact with this atom over here and with this atom over here. Okay, now this here we will just apply Newton's second law. Newton's second law tells me summation of Fx, we are only consider this atom S over here. Okay, summation of fx on this atom S is equal to its mass times the second derivative of us by dt squared. Now, what is summation of fx? If we take the x-axis to be in this direction, then I have F1 minus F2, this force here, F1 minus F2 is equal to, we agreed that this will be C times US plus 1 minus US minus C US minus US minus 1. Okay, because F1 is nothing but C, which is the spring constant, into US plus 1 minus US, and F2 is nothing but C again, US minus 1. So I hope this you can remember Hooke's law over here. Now I will just solve this equation. I have C into US plus 1 minus US minus C into US minus 1. Take C in common. So take C in common. What do I get? C will go outside. I will get US plus 1 minus US plus US minus 1. And this will give me C into US plus 1 plus US minus 1 minus 2 US. And this will be M d2 US by dt squared. Okay, let's continue. Now, how will US look like? In reality, US will be a function of, we look for a solution with all displacements having the time dependence, because this US, first of all, it depends on S itself, right? It depends on S itself, because depending on S, this displacement will be, and it also depends on time. Okay, so it depends on S and it depends on time. So I'm going to say, let US be U E I K S A E minus I omega t. Okay, perhaps you have seen this in physics 220 when we considered this as a sinusoidal function, and we said it is sine omega t minus ksx plus some phi function. Here we will take it to be exponential functions. Okay, the wave is defined only at the following lattice points: a, 2a, 3a, s minus 1a, sa, s plus 1a, etc. Finding the derivative, so I have now that US is U e to the I k s a e to the minus I omega t. We will find the derivative with respect to time, because I want to put it in this equation over here. I want to put C into US plus 1 plus US minus 1 minus 2 US equal M d2 US by dt squared. So the first thing I want to calculate d2 US by dt squared. So if before we get to d2 US, I can get dus by dt. This is equal to what? U, because it is not dependent on t, e to the I KSA, because again, this is a constant here with respect to time. Now, what is not constant is this e to the minus I omega. So I will have minus I omega, it will jump, okay? E to the minus I omega t. Now we take the second derivative of this. If we take the second derivative of this, which is here now, this minus I omega will be square, and minus I omega square will give me minus I omega square will give me minus omega square. So now what is my equation? I have M into minus I omega square U E I K S A E minus I omega t is equal to C. Remember from here, it's equal to C into US plus 1 plus US minus 1 minus 2 US. Okay, so I will come to, let's write it over here. So this is here, I have M d to US by dt squared is equal to C US plus 1 right? C of US plus 1. What else? Let me remember. plus US minus 1. So plus U of S minus 1 minus 2 US. Okay. Let's make sure. I think, yeah, this is it. Yeah, minus 2 US. Now, instead of, I will come here to US. US is e to the I. US is e to the I KSA e minus I omega t. What is US plus 1? From US, if I want to calculate U of S plus 1, okay, what will it be? It will be U e to the I K S plus 1 A e to the E minus I omega t. Okay, so this is US plus 1. US minus 1 will be the same thing, but here will be US minus 1, and US is US as it is. So now here what we get is here U, this is the first term, U E I K S plus 1A, so it is here, okay, e to the minus I omega t, plus U e to the I K S minus 1A e minus I omega t, minus 2 US. US is just as it is. Okay. Now we simplify by U e I K S A e minus I omega t. But what I mean by simplify is divide by, because in both equations, if you can see, I have here e to the I K S A e minus I omega t. Here I have e I K S A e minus omega t plus multiplied by e I K A. And here I have the same thing. So I will divide by this term everywhere because it is also here. Okay, let me erase a few things. So I will divide by this. So I will find it here, and it's also here, but there will be remaining e to the I K A, and here as well. But I will have left e to the minus IKA and here, okay? And then what do I get? I get minus I omega square is minus M omega square multiplied by M is minus M omega square. This thing we divide by it all everywhere. This will be equal to C into what will be left here is only e to the IKA. What will be left here is only e to the minus IKA. And here there will only be minus 2 left. Okay, now let me erase all drawings. I'm gonna use this identity, which is cosine Ka equal e to the IKA plus e to the minus IKA divided by 2. Okay, because you see here, I have e to the IKA plus e to the minus IKA. Okay. So if I plug that, instead of it, it will be 2 cosine Ka, right? This thing over here, which is e to the IKA plus e to the minus IKA, will be 2 cosine Ka. Okay, then we are going to continue. So here, what do I have? I have C, right, into, let me write it properly. I have C into 2 cosine Ka minus 2. So there is here minus 2. Now I'm going to use the other formula, which is, let's take minus 2 outside. If I take minus 2 outside, it will be minus 2C into 1 minus cosine Ka. Okay, and now I'm gonna use this formula over here, which is 1 minus cosine Ka over 2 is sine square Ka over 2. Okay, so we're going to use this thing. Now what will I have left here? Here minus M omega square is minus M omega square is equal to Here I have 2c, so the 2c is outside into cosine Ka minus 1. I introduced the minus inside, and this is how I got the opposite. Okay, and now this is implies, before I haven't yet used this identity. Okay, so we are still we just introduced 1 minus cosine Ka here. So I have minus m omega square is equal to c cosine Ka minus 1, implies omega square is equal to c over m into 1 minus Ka cosine Ka. The minus, we brought it to the other side. So now I have 1 minus cosine Ka. Okay. And now I use the identity that 1 minus cosine Ka is equal to times sine square Ka over 2. Okay, so 2c over m became 4c over m sine square Ka over 2. Okay, let me show you clearly how this happened. Okay, so I have 2c over m, 1 minus Ka, right? But what do I have here? I have that 1 minus Ka over 2, 1 minus Ka is equal to 2 times sine square of Ka over 2, right? So instead of 1 minus Ka, I will put 2 sine square Ka over 2, but there is already here 2c over m. So now I have 4c over m sine square Ka over 2. And finally, I get a relation between omega. I get a relation between omega and K, okay? And it is a function of C, that is the constant of the lattice, M, the mass of the atoms, A, the equilibrium spacing between any two atoms. C, M, and A are constants, okay? C, M, and A are constants, and they are a specialty of each crystal. So each crystal, they will tell you it's the constant of oscillation is C, the mass of the atoms is M, and the distance between two adjacent atoms is A. Okay, so they are a specialty of each crystal. Omega and K here depend on each other, and this we call a dispersion relation. Okay, so whenever we have omega as a function of K, that is the angular speed as a function of the wave number, okay, then we say, so this is a relation between the frequency, or this omega is a frequency, it is angular speed, angular frequency, whatever you want to call it, and the wave vector or the momentum K, we call it dispersion relation. If we plot it, it will look like this, because if from the function, if K is 0, I have omega equal to 0, because sine of 0 is 0, so omega is 0. And if K is equal plus pi over A, what happens if I put here plus pi over A? The A will disappear. I will have sine pi over 2. So omega will be 2 square root of C over M. And also from the other side will be omega equal to square root C over M. So the maximal value happened 1K equal plus or minus A. Okay, let's solve one exercise. Here actually we have to use all these functions that we mentioned. The fact that sine squared Ka over 2 is equal 1 minus Ka over 2. Omega equal to square root C over M sine Ka over 2. And also we will use this. So we are going to use the equation that we used, which is sine square Ka over 2 is equal to 1 minus cosine Ka over 2. Okay, we have used it before and we're gonna use it here. Maybe I put it here in the corner. Let's see if I can move it. Okay. maybe, okay, we will just keep it here. It's okay, I cannot move it further. And we will use the fact, we will use another identity, it will show up later, and we will use this cosine A minus cosine B is equal to this. Now, show that the total energy of the wave, so this is US, it is now a function, you can see it is a cosine function, U cosine omega t minus KSA, which propagates in a monatomic linear lattice of atoms of mass M, spacing A, and nearest neighbor interaction C. Show that the total energy of the wave is E, which is half M, which is this thing, okay? So the total energy is nothing but total kinetic energy. So we will start from this, total kinetic energy plus total potential energy. Okay, now what is total kinetic energy? It is half, if you remember, half mv squared. Here we will not say m will be the capital M, and here it is not v, it is actually d u by ds, sorry, du by dt squared. Okay, and this is the total. So we are going to do summation here over S of du by dt squared. Okay, and then we will do for the potential energy, it is half, this is spring constant C, and then we will do summation over S of what? Delta X, okay? Delta X here, you think of it as delta US. So I have US minus US plus 1 squared. Okay. Okay, you can see it clearly here in the solution. So we will start, energy is kinetic energy plus potential energy. This is summation over S of kinetic energy plus summation over S of potential energy, which is summation over S of half m dus by dt squared plus summation of half c us minus us plus 1 square. Okay, the m is constant, the half is constant, they come outside the summation, so I will have half m summation dus by dt squared. The c is constant, the half is constant, they come outside, and I get this thing. Okay, so I prove the first part. The second part, by substitution of us in this expression, show that the time, so what did we get? We get this function. Okay, show by now putting us in this equation, show that the time average total energy per atom is this thing. Okay, let's do this. So we are going to use what? Here I need dus by dt, so let's calculate dus by dt. Dus by dt is equal to what? It's equal to minus u omega, right, sine of omega t minus ksa. Right, so this is the derivative with respect to time, and I want it to square because it will enter here in the function as a square. So now dus by dt square is equal to nothing but u square omega square, okay, sine square of omega t minus ksa. Okay, by this we got dus by dt because we're going to use it. Now I need us, I have it. I need us plus 1, and then I need us minus us plus 1. So let's do it. So us plus 1 is equal to u cosine omega t minus k into s plus 1a, right? And this gives me what? This gives me u cosine omega t minus ksa minus ka. Okay, so this is us plus 1. Now what do I need? Also I need us minus us plus 1. So let me do it. So this is us minus, so I will calculate everything and then plug them in the formula and see what do I get. us minus us plus 1 is equal to u cosine of omega t minus KSA, okay, minus US plus 1, which is U cosine of omega t minus KSA minus KA. Okay, I just plugged US plus 1 here. Now they are giving me a formula that I should use. This is saying cosine A minus cosine B is equal minus 2 sine A plus B over 2 sine A minus B over 2. So I have now US minus US plus 1. Okay, as you see, you have U is common. So let's take, so here I have US minus U of S plus 1. Okay, is equal to, U is common, so U is common, into cosine of omega t minus KSA minus cosine of omega t minus KSA minus KA, right? Right. Now we are going to use this thing that cosine A minus cosine B is equal minus 2 sine A plus B over 2 sine A minus B over 2. Here I have cosine omega t. So if A is equal omega t minus KSA and B is equal omega t minus KSA minus KA, right? Because here I have cosine A minus cosine B, and here I have cosine omega t minus KSA, so this is A, and B is the other one. So if I have, this is A and this is B, I will apply the formula US minus U of S plus 1 will be U into minus 2 sine of A, which is omega t, minus KSA plus omega t minus KSA minus KA. This is A plus B, all of it over 2. Right? So all of it over 2. This is the first part, and then it will be multiplied by sine, the same thing, omega, but A minus B. So this will be omega t minus KSA minus omega t plus KSA plus KA over 2. And I'm gonna close my parentheses. Okay. Now we can continue here. US minus U of S plus 1, it's equal to what? It's equal to U minus 2. I can take it outside, right? So I will have minus 2U into sine of omega t minus KSA plus omega t minus KSA. So I have sine of 2 omega t minus 2 KSA minus KA, all of it divided by 2. Okay, right? All of it divided by 2. Times sine of omega t minus KSA minus omega t plus KSA. So these will cancel each other. So I will just have KA over 2. Okay. So I've reached this step. To continue from here, I will continue by doing that. From the first part, I will take 2 common. So I will have over here US minus U. Let me move this thing up. So I will have US minus U of S plus 1. This is equal minus 2U into sine of 2 omega t minus 2 KSA minus K over 2 is omega t minus KSA minus Ka over 2. Okay. Times, from the second part, I will only have sine Ka over 2. So we solve what is sine US minus US, US minus US plus 1. We got it to be minus 2u sine omega t minus KSA minus Ka over 2 sine Ka over 2. Okay, let's continue. In the formula, we want it to be square. So US minus US plus 1 square. Okay, so it will simply be, so we will take the square of this. It will be 4u square sine square of this times sine square of this. Let's go to the solution and you will see it. So here I'm showing you how I calculated US minus US plus 1. Okay, and we put, instead of cosine A minus cosine B, we use this formula. So I got US minus US plus 1 to be U into minus 2, whatever we calculated. And then the square of this will be 4u square sine square omega t minus KSA minus KA over 2 sine square KA over 2. Okay, now this is the energy, and we want the energy per atom. So we go back to our energy over here. Now we calculated everything we want to calculate. So now we just have to plug in the formula. I have here E is equal to half m dus by dt square plus half c summation US minus US plus 1 square. Now I'm ready to plug because I have what is dus by dt square and I have what is US minus US plus 1 square. But the question is to get energy per atom. So I will not do summation. I will only take that this is energy per atom is half m dus by dt square plus half c US minus US plus 1 square. Okay, and now I will just plug instead of dus by dt square, where it is, I did the calculation. Yes, dus by dt is this u omega sine omega t minus KSA. So square of this will be nothing but half m, the half m will appear, and then dus by dt square is u square omega square sine square omega t minus KSA. Okay, this will remain from the kinetic energy. From the potential energy, I will have half c into US minus US plus 1 square, which is here, and this will give me half c times 4u square sine square omega t minus KSA minus KA times sine square of KA over 2. So I plug this thing over here. Okay, this I plugged it for, or I plugged it actually over here. Okay, so it gave me this element. Okay, and I plugged dus by dt here, and I did the squaring, and it gave me this element. Okay, let's now continue. Let's remove, yeah. So let's continue. So now I have the energy is half mu square omega square sine square omega t minus KSA plus half c 4u square sine square omega t, etc. Let's continue. This is energy per atom, but the question is to calculate the time average total energy. So I need to calculate it over one period of time. Okay, so the average time over one period of time. What is the average of this? It is the average of the whatever has the t in it. So this is E is half mu square omega square sine square omega t minus KSA plus 2cu square sine square omega t minus KSA sine square Ka over 2, right? In order to get the average, we do the average of the whole thing, but half mu square omega square are constant, they go outside. So I will have left the average of sine square omega t minus KSA plus 2cu square, the average of the second component, which is here, omega t minus KSA minus Ka over 2, sine square K over 2. Again, this sine square K over 2 is constant, so I don't do average for it. But very important, this average and this average, if you calculate them, you will get half. Okay, so if you do this average, you will get here half and you will get here half. Okay, here I show you how to do the derivation. Okay, so you start by the average of sine square omega t plus alpha. In this case, it is omega t minus KSA. So the minus KSA is the alpha, okay, instead of carrying minus KSA all the time. Why it is equal to half? You do the average. This is the integral from 0 to period to 1 period of sine square omega t plus alpha dt divided by the integral from 0 to t dt, okay? Now, what is sine square of something? This is the function that I said we will use it again. It is 1 minus cosine 2 omega t plus 2 plus this thing, I mean, divided by 2. And down I have integral from 0 to t to dt, which is t, okay? Now I will do the integral for the whatever I have here. It is 1 over 2t, it goes outside, times the integral for 1 dt, which is nothing but the integral from 0 to t to dt, minus the integral from 0 to t to cosine 2 omega t plus 2 alpha dt. And this is 1 over 2t into t small t minus, what is the integral of cosine 2 omega t? It is 1 over 2 omega sine the function. Okay, 1 over 2 omega the sine function from 0 to t. If you plug the values, you will have sine 2 omega times period. Here you have to remember that omega is equal to pi f, which is equal to pi over period, implies omega times period is equal to pi. Okay, and now if I have here 4 pi plus 2 alpha, sine of 4 pi plus 2 alpha, it is exactly like sine 2 alpha. Okay, and from the other side also, I have 1 over 2 omega. If I put t, it will be 2 omega t, so I will get exactly, sorry. Now we're plugging the 0, so I will get 0 from here, okay? Plus 1 over 2 omega sine 0 plus 2 alpha, so I have sine 2 alpha. So I have now 1 over 2t, t minus 1 over 2 omega sine 2 alpha minus 0 plus 1 over 2 omega sine 2 alpha. Now, how much is this? And this will cancel each other because this is minus 1 over 2 omega sine 2 alpha, and this is 1 over 2 omega sine 2 alpha, and I will be left with 1 over 2 t, and this is nothing but half. Okay, so it is equal to half. And now if I go back to my equation, I have half mu square omega square times half. So I will have, this will give me half, okay, mu square omega square times half. So this is 1 over 4 into this thing, right? Because half times half is 1 over 4. Plus this thing is also half, and there is 2 here, so they will cancel each other. I will be left with cu square times sine square of ka over 2. Okay, so this is the average total, the time average total energy per atom. But now if I plug, so here it is, if I plug the fact that omega, if you remember from before, I have omega square here. I have omega square is equal to 4c over m sine square ka over 2. So sine square ka over 2 is m omega square. I cross multiply over 4c. Okay, so I come to this equation. So this is equal 1 over 4 m u square omega square plus c u square. Instead of sine square ka over 2, I will put m times omega square over 4c Okay, let me erase this and this. Okay, so now if you see this here, sorry, there is cu squared times m omega squared over 4c. The c and the c will cancel, and I will have 1 over 4 mu squared times omega squared, and here I have 1 over 4 mu squared times omega squared. So I will get this answer exactly. I will get that the average is, sorry, I will get that this average is this. Okay, so this is the solution. There is lots of math, I know, but I promise you, if you just sit properly and you apply these basic mathematical formulas, which again, I said one of them is sine squared Ka over 2 is 1 minus cosine Ka over 2. And we use the fact that omega squared is 4c over m sine squared Ka over 2. And we use the fact that cosine A minus cosine B is minus 2 sine A plus B over 2 sine A minus B over 2. And the integral of cosine alpha t dt is 1 over alpha sine alpha t. If you just use these 4 things and you do the math properly, all the math here is explained, but you can try to do it on your own. Okay, so that's it for today's lecture. We only consider bases that have one atom basis. Next time we will consider a bit more sophisticated version where we have 2 atoms basis. Okay, so that's it for today's lecture. Bye-bye.